Holy cow, everything's working. All right, so we haven't been together in quite a while, and it's good to see all these friendly faces, and thank you for coming out. Name tags, we're going to start doing name tags. It's gotten back to the board of directors that perhaps we're not quite the friendliest lot, and I promise you, if you aren't feeling welcome because I don't remember your name, I struggle with my dogs' names. I'll get them wrong. So, hey you is me trying hard. So, but we're going to do some name tags. Hopefully that'll help me anyway. We've got some copies of our newsletter up here. You're free to take home with you if you want to. If you don't get our newsletter electronically, there's a really good article in here about the electromagnetic spectrum. I'm going to do a presentation on that whole concept one day because that is the fundamentals of my hobbies start to finish. I'm also a ham radio operator. I play in the electromagnetic spectrum from DC to daylight. So there's that. If you have signed up to be on the President's volunteers list, and that's people that are committed to some extent to being involved in our outreach efforts, telescope, live observing sessions, what have you. If you've already signed up, you've got a packet of our very excellent sky charts, monthly sky charts. They're printed on waterproof paper, so dew is not going to affect them. And you'll have a name tag up here printed for you to wear when you're at one of these obsessions with the key title of telescope operator. So thank you very much for volunteering. The mouse pads, take one. I'm not sure what we're doing with them. So, and the officers and board of directors, if you're here, you get one too. There's everybody gets one that goes the extra mile. So, we are the Memphis Astronomical Society. We meet once a month and have most of the time a Zoom call. We're going to try to, we've been talking about meeting in person, how often we should. The Zoom meetings are a lot easier to set up and do and get to and what have you. So right now we have decided to try to make it a habit of at least on average once a quarter. But what we've also recognized is that parking at Rhodes when school's in is a challenge for some old fat people that have to walk all the way out there and make it in. So, and I'm talking about me, not of y'all. And so we have talked about maybe taking advantage of the summer months when school's out to have more meetings in person. And then, of course, the winter months being more on Zoom. We haven't worked it all out yet. Your input will help. So if you've got an idea, you've got an opinion, let one of the board members know about it, or send an email to any of us, to info@memphisastro.org, to president@memphisastro.org, or rick@memphisastro.org, and we'll get the message. This is us. We have a QR code. That means we're special. That means you can find us with your phone. I have a Rhodes College cup because I'm special. We have a web page for signing up. You can sign up to receive our newsletter, which is not too abusive. On average, once a week. We'll get to a meeting. There'll be a couple that go out around the meeting. We get to an observing session. We'll send the go, no-go calls out by email for observing sessions. So we try not to abuse email. And you can also sign up to become a member on this page. And quite honestly, membership is $25 a year. In today's world, that's nothing. That's a drop in the proverbial bucket. And if you don't want to be a member and you don't want to come to meetings, but you just like what we're doing, you can support us by joining and paying dues. So thank you very much for those of you that do that. We have a calendar on our website. Let's see if I got everything. April 12th, we have an event at Pinson Mounds. April 26th, we've got a solar observing session at Chucalissa. Where did mine go? There it is. Have I got it so far?
Got it so far.
26th, we also have Village Creek State Park at 7 p.m. That's a big one for us. We do that one twice a year and have for 30-something years that I've been around. So that's a big one. May 3rd is the MAS members picnic. So if you want to come to our picnic, join. See, $25. It doesn't cost money. You get a lot for your money. Did I miss anything?
You got it.
All right. And as a reminder, I haven't worked these details out yet. I've been really busy at work. The President's Volunteers list, I'm trying to create a better communication channel. Sending out an email to our distribution list that says, hey everybody, we're going to do this public event, we need telescope volunteers. And we don't hear from anybody about it. And suddenly, no people show up to 20 people show up, and we'll have anywhere from 200 people show up to look through telescopes, and we only got 2, or we'll have 3 people show up to look through 10 telescopes. So we're trying to do a little bit better job of managing that. I haven't figured this out yet. I've looked at a number of different medias and stuff. Bottom line is, most of them you've got to sign up to be a member to manage it, and I know nobody likes doing any of that stuff. Right now I'm looking at a Google Forms thing, which I think will work, and for feedback, you let us know that you're coming and what have you. But it's going to be an email distribution list that resides on my computer only. So I've also heard from a couple of people that the people on the list don't necessarily want their email address shared with everybody else on the list, so that won't happen. But you can always reply to me, and that'll get the message through. So anyway, that's where we're at right now. The President's volunteers list will be special people, as noted by these wonderful waterproof sky maps that are up here for the President's volunteers with their plastic name tags with telescope operator identification. Not only that, but we haven't figured out what we're going to do yet, but we're thinking a dinner or something, at least once a year, something along those lines. We'll figure it out and let you know, but we intend to make it to some extent worth your while. We have some new members this month. This is as of the last board meeting. We are no longer trying to keep up with who signed up in the last 15 minutes before the meeting started. That was always made getting ready for the meeting a little tough. So thank you to David Carroll, Vanessa Pratt, Aaron Culver, and Brett Johnson for joining MAS. Are any of you here tonight? That is not unusual. That's how it normally goes, and that's fine. Thank you for joining. Maybe you're on Zoom. All right. We have a newsletter. This is a wonderful production, and every month I'm amazed at how I mean, if nothing else, it just looks good. And Steve Wright, our videographer back there, is our primary producer and editor. He put in this wonderful article this month about the electromagnetic spectrum and some of the astronomy that happens outside of the visible light range. And there's a letter from me about being nice, and there's a notice about the picnic, and there's 5 or 10 more pages to go with this, including the monthly star chart and our calendar. So subscribe, be a member. You'll get this in your email every month. All right, the Meteorite has a classified ads section that no one has taken advantage of yet. I'm taking some vacation this week, and hopefully I'll have time to write some ads, because I've got a ton of equipment that needs new homes. The MAS has had equipment donated to it over the years, and we need to get rid of some of it. So I'll be putting some ads in there for that stuff. We've talked about having perhaps a swap meet one weekend. I'm not sure where or how we can pull that off, but keep an eye on the newsletter. We might have a swap meet in my driveway in the not too distant future. I think I have all, if not most of the stuff that belongs to the MAS. So. All right, the Memphis Astronomical Society has an astrophotography focus group. Get it to play on words, focus group, focus cameras and stuff. Not only that, but the file format used for astronomical images is called FITS, F-I-T-S, and so the MAS.FITS is a play, and they call themselves the Mass Fits. This is, they get online and have a Zoom meeting once a month. Everybody from people taking pictures through the eyepiece with their iPhones to Merrill Miller's setup to the telescope on top of the building, the physics building here at Rhodes, are people who collect data. That's what we call taking pictures for astronomy purposes. We collect data, and then after that we process the data. And it's that data processing that's a lot of fun and gets rather complicated. And so these people get together every month to share with each other the tricks and stuff for doing that. They've also supplied, for the second year in a row, photographs that they have taken and processed and printed and donated to Theater Memphis during the run of the play, what's it called, Silent Sky. And this is one of them. And the detail in this thing will blow your mind. And to think that a handful of people around here collected all this data and processed it, it's as good as Hubble stuff. I mean, it really is. These are a picture of the pictures at the theater, and so if you want to go see the play, I think it's on another week or two.
Through the 19th.
Through the 19th, thank you. And these prints are for sale at Benefit Theater. So if you want one, go buy one there. We may be able to get prints later ourselves. That right there it just blows me away. It might be gone by the time y'all get there. I'm just saying. So anyway, thank you to the Mass Fits for doing that. Excellent work. We have swag. We have Cafe Press will generate all kinds of stuff with our logo on it for you. Shirts and cups and mouse pads and stuff. So get your MAS swag at Cafe Press. There's a link to this on our website. We don't get any money from this, but it gives you an opportunity to show the world that MAS rules. Rah. All right, so I went through this back in February, and I wasn't able to give them their certificates then. 2 of them are here now. So, to Mark Matthews from the Night Sky, NASA's Night Sky Network, on behalf of them and the Memphis Astronomical Society, you are one of our outreach champions for 2024. There's your certificate and your pen.
Well, thanks, man.
Mylan, who has now stepped up into the position of Vice President of Observing, was our outreach chair last year, and too receives a certificate and a pen. Thank you, sir. Jeremy Veldman, last year's president, is not here tonight, but as soon as I see him, he gets that too. So, thank you very much, and on behalf of the Night Sky Network and the Memphis Astronomical Society, well done. All right, is that everything? I think so. All right, all the stuff's out of the way. We have what I'm going to bet money are 3 great presentations tonight from the graduating class of Rhodes College this year. We have black holes, galactic winds, and quasar spectra. I don't know what order they're in. I don't know which one of these people is which. So who's going first?
Jack's going to go first.
All right. And you are?
I'm Jack.
Jack? Let me...
So, Jack Harper, senior physics major here at Rhodes, econ minor. I'm involved with the chess club here at Rhodes. I'm president of Astronomy Club. I'm a chess coach and going to grad school for economics. And I'm going to tell you guys a little bit about my research that I did here at Rhodes studying the winds of the Makani galaxy. Alright, so a little bit of an overview about the Makani galaxy. It means wind in Hawaiian, and it was discovered by one of the professors here at Rhodes, Dr. Rupke. Some of you may know him. It's very interesting. It's 100 kiloparsecs in diameter, which is about 300,000 light years-ish. It's 6.6 billion light years away from us. And it's really cool because it's producing winds that are traveling at thousands and thousands of kilometers per second.
Whoa.
Yeah. So why are we studying Makani? Well, because it's so far away, it gives us a glimpse back in time. So some of you may know, the farther away a galaxy is, the farther you're seeing back in time because of the way light travels. So Makani is 6.6 billion light years away, so we're seeing 6.6 billion years into the past when we're looking at Makani. So studying these faraway galaxies helps us understand how galaxies evolve over time since they first formed towards the beginning of the universe up until now, where we are today. So Makani gives us a very unique perspective because of how active it is. These winds are very unique and unprecedented, some of the fastest and largest winds that we've seen from a galaxy during this time period. So here's an image of Makani on the left here. As you can see, there's like a black little blob in the center. That's where most of the stars are located in Makani. But you can see these big, colorful blobs that are coming out from the center of the galaxy. These are all winds. So as you can see, most of the surface area of this galaxy is wind, which is very cool. Next to it, I have a little picture of our closest neighbor, Andromeda galaxy. The Andromeda galaxy is one of the biggest galaxies in our local galactic cluster. It's not even half the size of these winds. So the winds extend out about 100 kiloparsecs. Andromeda is about 45 kiloparsecs in diameter. So just very big, gives you a perspective on how active these winds are. So what might be causing these winds? Winds are usually caused from rapid star formation in the galaxy. So as gas and dust form together and then they fuse and ignite into a star, it pushes gas out and accelerates it. So as lots of stars are forming in the galaxy, it's accelerating lots of gas over and over again. Could also be secretions from a black hole. Black hole has a lot of gravity, so the gas and dust that's orbiting very close to it is being churned around and shot up around the galaxy. But there's also another unique part of Makani. It's that it's not just one galaxy, it's two galaxies that collided into each other very recently. So lots of gas that was created during the collision and is now being formed into stars and orbiting that central black hole. Alright, so how do we study a galaxy like Makani? Well, you can't really see Makani because it's so dim and it's so far away that it's been redshifted due to the expansion of the galaxy. So we have to use different filters to capture certain wavelengths of light so we can study the different parts of it. They allow us to study different parts of the light spectrum that might be coming from the galaxy. And the winds in Makani were hypothesized to have a lot of hydrogen in them. So we're going to choose a filter with a lot of, with the spectral lines of hydrogen. And that's how we're going to study these winds. So how do the filters work? I think they work a little bit like our eyes. So our eyes let in a certain wavelength, a certain range of wavelengths, and the more light that it lets in, the brighter that object's going to appear. The filters work the same way, except instead of the visible spectrum, we're going to use the ultraviolet spectrum to study the emission lines of hydrogen, which we use the F150 filter for on the Hubble Space Telescope. We're going to study an emission line of oxygen, which is going to correspond to the F165 filter. So this is a 165 nanometer wavelength. And then the F814W filter, this is going to be infrared, and this is kind of like our control, since it's not studying anything in particular, just the infrared spectrum of Makani. Alright, so when we receive data from the Hubble, it comes in a unit called a flux. So a flux is just how much energy is coming through the telescope in a given spot. So we don't really, as astronomers, we don't really use flux for some reason. We just didn't want to make it easy. We use the magnitude system, which kind of reverse of flux. So more flux will be lower on the magnitude scale because that means it's brighter. And the lower the magnitude, the brighter the object. So a really bright object will be in the negative magnitudes. A really dim object will be in the positive magnitudes. So as you can see here, just a few examples of like where different objects are on the magnitude scale. So first job, we had to convert these fluxes into magnitudes. And here's the maps of the galaxy that have been converted into magnitudes using the different filters. So on the left, we have the F814W, and the 150, and the 165. And then we have the magnitudes. And as you can see, it's all very dim. It's like in almost 20 or over 20 magnitudes, so very, very dim. Wouldn't be able to see it with even a telescope. Had to use the special data from the Hubble for this. And let's get into the gritty details of how I analyzed the magnitudes of these winds coming from the core of this galaxy. So the gritty details. First I had to reduce the data. Here's an image of Makani, the blob in the center. That's the core of Makani. I had to erase the other galaxies in the image, so find where the other galaxies were, and take them out of the image, and then reduce the noise in the image. So this was a very difficult process. Took over half my summer, actually. But and then I used a method called aperture photometry. So in aperture photometry, you're going to start at the center of the galaxy with a very small circle, and that circle is going to add up all of the fluxes from those pixels. And you make the circle bigger and bigger, and it's going to gather more and more fluxes. You can actually see with each radius of my aperture, it gets more and more flux in there until it starts to even off. And that's how we know how big the galaxy is and what the magnitude of the galaxy is. So we start in the center, we get more and more flux, and as we reach the edge of the galaxy, we don't get any more flux as we make our aperture bigger. And so this is how we got the data from the center of the galaxy and how big the winds extend and like how bright they are. So that's what I did this summer. Thank you guys for listening, or not this summer, but a couple summers ago. Thank you guys for listening. I hope you learned a little something about Makani.
Any questions? Oh, come on now, don't let him off. Look, that easy. That was excellent. Thank you very much.
So with the filters, you know that it's redshifted.
Mm-hmm.
You have shifted filters, or are they just wide enough to capture everything you need?
So yeah, we've accounted for the shift. So the hydrogen line, the hydrogen spectrum line is not actually 150. It's accounted for that redshift.
And that's
Excuse me.
You know, the pattern of hydrogen spectra is pretty specific. If it's not where it belongs in the spectrum, but it's way over here, that's how you know how far it's redshift. And that's how you pick the filters.
You used the filters. What did you use them on? Or were you using to look at the galaxy?
Oh, this is the Hubble Space Telescope. So,
Okay.
Those
data sets, by the way, are available to the public.
Yeah, I mean,
pull down and work on.
That's how this was discovered. Dr. Rupke and some other scientists were just kind of sifting through this, and they noticed that this was kind of anomalous with these winds while they were sifting through the data.
Do you have velocity maps of this galaxy?
Sorry?
Do you have velocity maps?
Velocity maps?
Yeah.
I do not. I could ask Professor Rupke because I think that there is one, but that's not what I did. I wasn't measuring velocity.
I want to see some velocity maps. I can't do it. My research is different, but I got some.
Amos?
Very cool.
Ask me about okay.
What's next? Which one?
Is this one? Is this one?
Here.
I don't know why that came out like that.
Stick that in your pocket. Let me pinch your shirt. There you go.
All right. I get to go?
You got the clicker?
Oh.
Right. Goes through them, left goes back, the green's the laser pointer.
Okay, all right, thank you. All right, so hi everybody, thank you for having me. My name is Jany, and I'm a senior here at Rhodes. I'm a physics major and a math and comp sci minor. And today I'll be talking a little bit about 21 centimeter cosmology and astronomy, and more specifically my research last summer at the University of Texas at Austin called Capturing Cosmic Dawn, using ultra-efficient maps to capture, using ultra-efficient programs to capture maps of the universe during cosmic dawn. Okay, so to start, I kind of want to map out what cosmic dawn is and why we really care about this time period. So cosmic dawn, I have it shown in this box right here. It's the time period from about a redshift of 25 to about a redshift of 15. And this is the period in our universe when the first stars and galaxies really began to form. And this process started about 13.5 billion years ago. And the reason we care about this is because we actually don't know a lot about this time period as of right now. It's very difficult to observe this time period with our current technology and telescopes. But if we do end up being able to detect this time period, we'll be able to learn a lot more about how the first stars and galaxies formed, and that will hopefully let us confirm different things about our current cosmological models, as well as how stars and galaxies like our own formed, and how they will continue to evolve in the future. So I kind of want to talk about what is 21 centimeter cosmology. So 21 centimeter cosmology is based on the 21 centimeter signal, which is a specific signal of light that is given off by neutral hydrogen. And right here I've got this diagram kind of showing off how that is created. We have just a neutral hydrogen atom, and some outside interaction causes the electron spin to flip, which gives off a photon that has a wavelength of 21 centimeters. And so because this time period, cosmic dawn, is so far back, it's actually very difficult to observe this. We can only observe this with radio telescopes. And because it's so far back, all the light from this time period is very faint, so we currently don't have the radio telescopes that are sensitive enough to detect this time period. And so my research is kind of helping us to prepare for when we do have this technology available. And using this 21 centimeter signal, we'll be able to detect an abundance of neutral hydrogen in this time period of the universe. And with this, we'll be able to map out how galaxies and large-scale structure formed and how it evolved over time. So this is my research right here. So to start, I used a Python software called Zeus 21 that basically gives us a kind of low-end simulation of the universe at large. And from this, I'm able to calculate a 21 centimeter signal, which is this curve right here. Now, as you can see, this doesn't really tell us a lot about the large-scale structure in the universe, how galaxies and black holes and things formed. But my research is kind of taking this and evolving it to the point where we can create maps that visualize the universe during cosmic dawn. And so to start, I made a general simulation of the 21 centimeter signal, and from this I got this power spectrum right here. Now what this power spectrum is able to tell us is it gives us an idea of the general fluctuations of the 21 centimeter signal over time, as well as the scale of the structures that are given off this 21 centimeter signal. And from this power spectrum, we're able to trace back all of the biggest factors that give us the 21 centimeter signals that the simulation predicts. So this right here is kind of a map of what we were trying to do. So we started with the power spectrum over here, like I said before, and using another Python program called PowerBox, I was able to take this power spectrum data and generate actual maps like this, where we can visualize all the different large-scale structure in the universe. And once I did this, I had to then reverse the process, so use this map to get a power spectrum back and kind of make sure that there wasn't any errors with the way it was being calculated. And so once that whole process was finished, I was able to get all the results we wanted referring to the 21 centimeter signal. So this right here is kind of the first results, where we were able to kind of pinpoint all the main contributing factors to the 21 centimeter signal. So right here we have density, so just overall where the most matter and galaxies and things like that are concentrated. Excuse me. And then right here I have a kinetic temperature map, which basically just tells us where the hottest gas ends up being. And this right here, this last graph, is just the Lyman alpha radiation. So it's basically just a measure of where the stars are giving off the most radiation in this early time period of the universe. And so as you can kind of see, these maps kind of overlap each other. So right here, these greener parts are the denser areas. And so as you can see right here, we have a big hot spot, and as well as over here in the kinetic temperature, they all kind of point to the same areas in the universe. So this is very helpful in calculating mapping out the large-scale structure of the universe. And so right here, these are the final results, kind of what we were able to do once we had all these different components. And I kind of want to, the main features of these graphs is these color bars right here. So these are the 21 centimeter signals that we calculate at different points in the universe. We start off right here at about a redshift of 24, which is about 180 million years after the Big Bang. And we go right here in this order all the way to a redshift of about 13, or about 300 million years after the Big Bang. And so the most important features of these graphs is these numbers over here on the color bar. So these correspond to the 21 centimeter signal. And the bigger these numbers are, that refers to how much neutral hydrogen is abundant, and how much of that signal is able to be perceived by future telescopes. So as you can see right here, we have in this earliest time, we don't have as much large-scale clumpy structure. It's still kind of stars and scattered black holes and stars that haven't formed galaxies yet. And as time goes through, we see that not only is the signal increasing, the numbers on the color bar, we can kind of see the larger scale structure take form and materialize into what we see today. And this right here, this is the same as that 2 in 1 centimeter signal that I showed at the very beginning, kind of the initial output that we use to create these maps. And I kind of have, I don't know how easy it is to see, but I kind of have them mapped out. So from right to left is kind of the same order as these graphs. And so you can see how the magnitude of the 2 in 1 centimeter signal kind of fluctuate throughout time right here. And so yeah, with these maps, we're able to quickly generate large-scale simulations of the universe. And the nice thing about this project is that these maps are able to be created very fast and efficiently. I was able to do it just on my my MacBook over there, and it took about a minute to run a simulation kind of like on the scale of this. So yeah, when in other research, these require like supercomputers that take months and weeks and months to actually generate. So that's one of the kind of upsides to this research. And kind of the future implementation of this would be to once we have telescopes that can actually receive the signal, like these ones shown here. Right here, this is the square kilometer array, and this is the Hera radio telescope array. And these will be able to give us 2 in 1 centimeter detections. And with these detections, we'll be able to compare to our current cosmological theories and kind of rapidly compare to find out which of our predictions were actually correct. So yeah. And kind of what this will mean for astronomy is that we'll be able to map out the early evolution of the universe. And like I said earlier, with this information, we'll be able to solidify our different theories and figure out how the universe came to be what it is today. And hopefully we'll be able to get a glimpse of how the universe will unfold as time goes on. So yeah, that was kind of my main project. Right here I've got a couple pictures of my time at the University of Texas at Austin doing this research. They let us go on a visit to the McDonald Observatory over in West Texas, and I was able to see a lot of cool telescopes. This right here, these two images are of the 2.8 meter telescope that they have over there, and this one right here was they allowed us to mess with the I believe 0.9 meter telescope, and they let me replace the liquid nitrogen that they use to keep the lenses as cold as possible for their observations. So yeah, overall I had a great time, and I'd like to thank the University of Texas at Austin for giving me this opportunity, as well as NSF, and also all of my friends here at Rhodes that helped me get to this point. So yeah, I'm taking any questions.
So is it possible to detect any correlation between the maps you generated and the cosmic microwave background? Is it laying out where it correlates at all?
Yeah, so that's actually one of the most important parts. So in a lot of the timeline of our universe, the cosmic microwave background ends up drowning out this 2 in 1 centimeter signal. But luckily for us, this cosmic dawn time period, the abundance of neutral hydrogen is actually able to overcome this cosmic microwave background, and we're able to detect it at its strongest point.
The square kilometer array, where is that?
I believe it is being made in southern Africa, and I believe parts of Australia.
Yeah, half in South Africa and half in Australia.
That's what I thought was in Australia.
There was actually did some work way back in like 2010 for some SK planning stuff. Back then we weren't sure whether it was going to be one or the other. They went with the compromise solution where the low frequency component's going to be in South Africa, and the high frequency component's going to be in mostly in Western Australia.
Right.
Yeah.
Cool. Very cool.
So I'm one of the suckers who runs these weeks to months supercomputer simulations. I'm very curious as to I have some guesses as to how Zeus 21 works, but what's it doing differently than like the standard n-body simulations that makes it so fast?
Yeah, so I believe first off, it kind of makes generalizations and approximations of kind of the low-level physics, so like particle interactions and things of that nature. And it also makes approximations. That's a little bit of my work was kind of for the components like this. They kind of they use general approximations instead of like more accurate and drawn-out simulations like the ones that you would do, I imagine. And that kind of lets us run down the computation time.
So does it like sort of evolve step by step forward in time, or is it kind of a way to take a 21 centimeter map and just directly produce a like from CMB to 21 centimeter in kind of a single step?
I believe it's more of a single step kind of process.
All right. Cool.
Yeah, thank you. All right, well, yeah, thank you.
There we go. And how do I, laser, got it.
And right is advance,
And
left
then-
is backwards.
Gotcha. All right, so my name is Ryan McCrory. This is research that I did in the summer going into my sophomore year. So this PowerPoint is actually mostly over 2 years old. I updated it a little bit, but there's a lot of details in here that you could research the project and find more up-to-date data. That being said, I will be presenting on the work that I did specifically. So as mentioned, a lot of this is out of date. I should also mention I'm going to the University of Arizona for graduate studies in optics. Alright, so my work was on quasars, and specifically spectral line fitting, and I'll explain what all those terms mean. And the fun part, we use the James Webb Space Telescope. I did this work with Dr. David Repke here at Rhodes College. So the topics that I will cover loosely, I'll first start out with a general overview of supermassive black holes and quasars. I'm actually going to move over here. Yeah, that's better. I can see the slides on this monitor and maintain eye contact with you guys. Oh, something else I should mention, feel free to stop me if you have questions at any time. I would not mind that whatsoever. I'll be covering supermassive black holes and quasars. I'll be covering the James Webb Space Telescope and IFU mode, which stands for Integrated Field Unit. I'll explain what sort of data that produces and what we can expect to learn from it. I'll go over the Q3D project in more detail and the goals of the project in general, and my specific contribution will be the last portion. So, start out, what is a quasar? So a quasar is an object which is effectively all of the gas that is surrounding and accreting supermassive black hole. So as most of you know, most galaxies are theorized to have supermassive black holes. This is a quasar, a near one called Markarian 231. Actually, this is the nearest quasar to Earth. So this is a Hubble image. We've got a pretty good idea of what the system looks like, and the bright star-like thing in the center is actually the light from the quasar. So, the L bowl, that is notation for the bolometric luminosity, which is all of the light in the broad spectral emissions of the electromagnetic spectrum, so all the way from the radio to the gamma. And that luminosity is on the order of 100 billion times the light coming out from the sun. So you can imagine 100 billion suns in about the area of the immediate vicinity of a supermassive black hole. It's very intense. This impacts the entire morphology of the galaxy as well as star formation, etc. Something else I will mention later is that we see most quasars from a near vertical viewing angle. So what we have here is the unified quasar model. This generally describes the morphology of gas and dust around the supermassive black hole. So we have in active black holes, we have an accretion disk. I should mention also that quasars only form in systems where the supermassive black hole is actively consuming matter. So a lot of galaxies have quiescent supermassive black holes, like our own, right, at this period in time. Our supermassive black hole is not consuming matter at high rates, so our center is not glowing at nearly the intensity as the one in Markarian 231 here. But galaxies change with time, and we have had periods with intense supermassive black hole activity, which would have produced quasars. And actually, in the last few 100 million years, it's theorized that happened. As mentioned, extremely bright. They outshine entire galaxies. So here is a model of viewing angles, and there are two main classes of quasars. There's a radio quiet version and a radio loud version. And basically the difference is, I believe, in the jets. I did not study the theory of this as much. I studied more the observation. But I believe it is just in general the emissions that we see from Earth. And the classes of quasars are actually defined by the angle with which you view them. So Seyfert galaxies kind of correspond to the narrow line and broad line radio galaxies. I'm kind of surprised that this graphic doesn't call them class 1 and 2 quasars, but either way, broad line and narrow line, those are different spectral regions which come from different areas of the quasar. The narrow line comes from the outer parts of your outflows. So these clouds over here represent that. The reason why it's narrow is because it's farther out from the black hole, so the velocity ranges of that material, they're pretty narrow. Whereas the broad line is this region here, and it's stuff that's pretty well influenced by the black hole's gravitational field. So the velocity gradient is really high, because you can imagine as you go close to the black hole, you have things orbiting at really high speeds, in addition to things getting propelled out at very high speeds as well. Here is actually an image from the Event Horizon telescope. And this is of Messier 87, which is a really large irregular galaxy. And this is of the outflows of that system. So you can see this is the famous Event Horizon images that a lot of you guys have seen. But what I bet that many of you haven't seen is that with relatively the same instruments, they also did surveys on the outflows, and you can see the jets which emanate from the system in X-rays and in radio, so it's broad spectral. And what I really want to point your attention to is the conical structure here. That's the sort of stuff that we're expecting to see from spectral data, and the stuff that we do see. So, again, quasars are on the order of 100 billion times brighter than the sun. The supermassive black holes are of masses on the order of 1 million to 10 billion times more massive than the sun. Oh, something I should also mention, this notation here with the circle with a dot in the middle, that is relative to the sun. So solar masses, solar luminosity, that's just a notation that astronomers use to compare it to something that we know. So, why would we use the James Webb Space Telescope? So, you can see, actually, a fun detail about JWST is that it has a mirror which is plated in gold. The reason for that is because gold plating is really well responsive in reflectivity to infrared wavelengths. So if you had plated it with silver or something very similar, it wouldn't reflect as well in infrared. Whereas gold is very reflective in those wavelengths. So that's the reason for that design choice. But the atmosphere absorbs a lot of infrared. So the reason why we need to put specifically mid-infrared instruments in space is because we can see those wavelengths, which is fantastic for science. Additionally, this is optimized to observe dim distant objects because, as you guys in MAS Fits know, big light bucket means that you can see dimmer things and farther away. So that's what JWST is there for. It's a 6-meter aperture. It's great for those purposes. In addition, those guys at MAS.Fits will also know that atmospheric distortions are a real thing for very small angular objects like planets. So we don't have to worry about that in space. Cryogenics, so this is actually, I believe it's liquid helium cooled. So it's cooled to about 2 Kelvin if I remember right, which is very close to absolute zero. You need that for infrared because things, even at relatively cool temperatures, like liquid nitrogen temperatures, glow in infrared wavelengths, which will interfere with your detectors. So I bet that you guys will appreciate this slide. Dark Side of the Moon is an amazing album. I love it. But, of course, it's a representation of a prism which separates white light into its constituent visual components. That's effectively what a spectrum is. So you take something, albeit a prism or a diffraction grating, and you put light through it and separate it into individual wavelengths. The reason why it works for a prism is because a refractive index is dependent upon wavelength. For gratings, it's something slightly different, but similar effect. You can use a spectrum to describe an object's chemistry, temperature, velocity, the mass of a black hole, which is what I do in this study, the luminosity of the object in certain areas of the spectrum, etc. And here's actually a spectrum from the James Webb Space Telescope. This is of an object called J1652. It's a quasar, very, very bright. And this actually is a feature that I'll note. This is a gap in the detector, which I'll explain in the next few slides. This is in all JBST spectra. It's just a design feature. And also the things I note here, also you might notice that this is in the infrared. This object is very redshifted. It's got a redshift value of about 3. So all the wavelengths are multiplied by 3. And you might recognize hydrogen alpha for anybody who does astrophotography or solar observing. That's actually shifted well into the infrared now. And then O3, you guys will also recognize from astrophotography. And then there's some other lines like helium-1, sulfur, and then the rest of the Balmer series of hydrogen, beta, and gamma are represented there as well. I'll go into greater detail onto what those mean specifically for this object. Here's NIRSpec. I just added this slide about 10 minutes ago. So the optical design of NIRSpec is very complicated, clearly, but the part that you should note is the integral field unit. That's the IFU unit which we used, and it is used to gather spectra on a pixel of an image. And I'll go over what that means and how we can generate, instead of a 2D image, a data cube with a third dimension. And here's the explanation for the detector gap. You have an array of detectors. This is actually just 2 of them, but there are 4. There's 2 more down here, and there's a gap right here, which actually allows, or it makes the telescope blind to a certain region of the spectrum. Not a problem for us, but if it fell on an inconvenient redshift value, we would miss a critical spectral line potentially. Here's what the raw data looks like on the imaging sensor. As you can see, it is a mess. That's why we have computers, to make this not a mess. The data reduction algorithms are very, very elegant. Alright, so here is a data cube. So you can see that we have an image on the cross-section of this cube. So we have dimensions x and y for each of the pixels, but we also now have a dimension lambda. And what you can do is you can take each of these pixels and basically get a waveguide, so like a fiber optic cable, and grab the light from that and get it through its own diffraction grating, and then that is scattered onto an imaging sensor. So you can imagine each one of these spectra is from a pixel of that image. And then from there, you have a 3-dimensional data set. So as you can see, here's our galactic nucleus. This is a very bright point source. And you can see the spectrum is represented in this cross-section along, I guess this would be the x-axis. And you've got lambda, or wavelength, here. You can see that the brightness varies with lambda as well. Like you have an absorption line here, an emission line here. And that is very useful for us to figure out which areas of the galaxy are moving at what velocities and what they're made out of, in addition to temperatures, morphology, all that stuff. And you get that all with one, albeit really complicated, data set. So what is Q3D? So Q3D is an international collaborative which focuses on the study of quasars, specifically with James Webb, using the integral field unit instrument. And we developed a package called Q3D Fit, which analyzes integral field data and gets valuable characteristics from the spectrum, such as isolating the nuclear spectrum of the quasar, which is, of course, the black hole itself, and subtracting that from the entire image field, and just obtaining the galaxy spectrum, which is really useful for morphology, outflow studies, etc. So we studied 3 quasars in this proposal, F2M 1106, XID 2028, and J1652. I'm focusing on these 2, F2M and J1652. This one, at the time that I was doing my research, we did not get data from. By this point, they do have data, and there's actually a published paper as of a few years ago on XID. So what work was done? So this is specifically my work on the program. The first thing I did over the spring of my freshman year into the summer was develop a line list program. And what it would do is it would take known emission lines and convert them to either microns or another unit called angstroms and redshift them for whatever object we wanted. It was a function which would generate these tables. It ended up being useful just for the bare bones of Q3D fit. So I developed that, and I credited a lot of the sources I use in this heading. It comes from a bunch of different public NASA data and NIST data, if I remember right. So, fun acronym. This is a program that we compared Q3D fit to. It is called Bayesian AGN, Active Galactic Nucleus, Decomposition Analysis for SDSS, Sloan Digital Sky Survey. It's an instrument used to survey the entire sky. Spectra, or BADASS, which is the best acronym ever, hands down. And what it would do is it would fit Gaussian distributions, like these guys here, to a active galactic nucleus core spectrum. So here's an instance of the output. This is on F2M 1106. This is at a redshift about 0.435, so compared to J1652, it's relatively close to us. This is actually not from James Webb. This is from the BOSS spectrograph, and I apologize. I totally forget which observatory the BOSS spectrograph was installed on. I forget if it's Gemini or if it's SDSS. You would probably know.
It's on SDSS.
Okay.
I think it's on SDSS.
Gotcha.
Yeah.
But the bolometric luminosity, I apologize for the strange units. We use a CGS system, so instead of joules, we use ergs, which are about, there are about 10 to the 7th ergs in a joule. Very small unit, but either way, this is about the equivalent of 10 trillion suns in luminosity. So extremely bright. This is what's called a red quasar. Basically what happens is you have a bunch of dust between the quasar and us, and like the sun turns red during sunset, the blue light is extinguished by the dust and we see mainly the red light. So it's an interesting galactic structure. Another thing I should mention is that this is a 2 arcsecond diameter field of view to obtain this nuclear spectrum. So for those of you who do astrophotography, that's very small. And then this is the object, which is the fun one. So this is J1652, redshift of about 3, so really far. It has a bolometric luminosity of about 10 times higher than F2M. So extremely bright and a very chaotic object. And this was actually taken with the James Webb Space Telescope's NIRSPEC instrument, the one I showed you guys earlier. And velocity maps, got some. So this is specifically with O3. So the blue portion here is going towards us, and the red portion is going away from us. You can see how the morphology changes, of course. The jets are going different places, so different areas glow at different redshifts. And here is a general overview of what the object looks like. I'll flip back aside real quick. So I obtained this from hydrogen alpha. I just took some region of wavelength, I took a median, and I got this image. It's relatively respective of taking a hydrogen alpha filter and taking a monochrome image. I just colorized it because, quite frankly, it looked cool. And this is the explanation of what the structure is. And I apologize that it's a little smaller on the board than I intended, but we have shocks on the right and left side, and interestingly, a whole bunch of companion galaxies. So you can see that there's a dot over here somewhere. It's kind of faint. You guys can't see it. And I believe, yeah, here's another. That correlates with a companion galaxy. And then there's a huge tidal tail that's outside of the field of view, which is believed to have existed from a merger or an interacting galaxy. So I did some numbers while I was on the project. I used BADASS to make this entire this Gaussian fit to the spectrum, which was obtained by JWST. And all these colors represent different structures, but the one that you guys should note is this teal-colored, very broad distribution here. This correlates with hydrogen beta, which is a little more on the green side to hydrogen alpha. It's emissions which are from the broadline region, so the stuff that's very close to the black hole and orbiting around it effectively. And this is so broad because of the Doppler shift. So the stuff is moving at a very wide range of velocities. And what that correlates to is a very high mass. So I ran some numbers. These were very preliminary, and the figures have changed since then. But it's on the order of 1 billion times the mass of the sun. As far as supermassive black holes go, this thing is gigantic. like terrifyingly so. So this has been updated, but last I heard, it's on the order of 1 billion. Solar mass is a few billion, so still very, very big. That is the end of my presentation, and I'd be more than willing to take questions if you guys have them. All right.
I'm very curious, what kind of optics problems are you planning on working on in grad school?
Ooh, good question. I'm not entirely sure yet. That being said, I'm interested in ultra-fast lasers because it's pretty cool. In addition, more classical optical systems, so building stuff like near spec. So these sorts of really complicated stuff on an optical bench interests me. I'm fairly new to optics, so I'll take the first year to figure out what I'm doing. I'm on a fellowship which pays for my first year without a research assistantship. It's pretty nice, actually. Arizona's got a good program. Any other questions?
10 years ago, I thought somebody should build. Actually, I think I read a paper about somebody was developing a camera, and they only had 4 pixels built at that time that would actually read the energy of the photon that hit it,
right,
and be able to determine its frequency and therefore its spectrum. And I think the idea was to ultimately build a camera that would actually read spectra in the image. Obviously, that never panned out. This unit is using, they're basically taking a fiber optic set and pulling each pixel off and doing a separate spectra of it, right?
I believe so. I have to look a little bit more into the optical structure, but it's a waveguide of some kind.
Now I've got to go look at it.
Yep.
Because I find it incredibly interesting.
Oh, absolutely it is. And the data you can gain from that is extremely valuable. Like you take albeit a very long snapshot of something, and you get spectral information at each pixel. It's great.
I downloaded all the data from James Webb for the M42 Orion.
Oh, really?
And I
Nice.
want to process that infrared data into something visual just to see what it looks like.
Oh, I bet that's going to look beautiful.
It's getting interesting.
Oh, yeah. And I mean, the structure is going to look completely different than it looks in visible light. I mean, you can see through it a lot better.
Was the first trick.
Yep.
So.
That's interesting. Super cool.
So near spec Rick might be using something a little bit lighter because of the whole like size weight constraints in a space telescope.
Yeah.
But typically for Earth-based IFUs, what ends up happening in almost all of them is in your optical plane where you normally have the plane of the CCD,
right,
you have an array of basically heads of fibers, optical fibers.
Right.
And then those all split out to an individual spectrograph connected to each individual fiber.
Right.
Just because we can't miniaturize the spectrographs enough to put them close enough, but typically, yeah, you've got a fiber on the scale
So what
of
are
like.
they doing here?
I think it's probably something similar.
I think so. I got to look at it closer.
I'm not as familiar with the space-based stuff because they're
Oh, do we
hard to get a look at that stuff.
Oh, yeah. Something interesting I should point out.
I've never been in the same room as any of the JWST equipment, but I've been in the same room as like some SDSS plates and stuff.
Actually, believe it or not, NIRCam, so the near-infrared camera, not the spectra scope over here, but that was developed partially at Arizona.
Cool.
So it was with them in north of Grumman. So it's pretty cool. But yeah, something else I should point out is this micro shutter unit. So they have a whole bunch of really tiny, I forget the scale, I'm sorry, but I think it's on the order of micrometers. Really tiny shutters that cover each individual pixel on the integral field unit. So if you want to take pictures of exoplanets, you can just block out the light of the star. It's really cool.
Very cool.
Yeah, the instrument you mentioned, BOSS, on the SDSS. SDSS kind of had a precursor idea to these IFUs, where rather than having a cluster of fibers that was essentially like the pixels in your CCD, they would, for every time they wanted to do this, they would have they know they're
I know where I'm getting
at
at.
this point in the sky, and there's 25 galaxies at random locations. So they would have a sheet of aluminum about this big, the aperture on the camera, or the optical plane. Just drill, 25 holes. Plop, plop, plop. Fibers go in each of them. So there are probably on the order of thousands of SDSS plates. It's kind of a thing for astronomers to collect these things.
I got some from AAS actually.
Yeah, they usually
they're great.
At AAS.
It's so cool.
But
where they drill a hole for each galaxy.
They drill a hole for each galaxy and then stick a fiber in. Yeah, so you only end up getting a single spectra for the galaxy, but it's cheaper than point at one, point at one, point at one, point at one. Yeah.
And they have a machine shop on site, and they have people who like put those fibers in manually. It's kind of cool, actually.
Yeah.
I've heard of
one very, very tired drill press.
Oh yeah, I've heard of other systems. I forget on which observatories, but where they have those fibers which are guided by actuators.
Yeah.
I forget.
Starbugs.
Yep.
Yeah. They kind of migrate around the back of the focal plane, moving the fibers.
It's pretty cool.
Yeah, I worked at the company that developed the first adaptive optics telescope.
No way.
Bobbitt Associates in Cambridge.
Wow.
And I worked with them for about 15 years on some technology that we developed for FedEx.
That's so
But the fun part was I got to bring home the first Hartman wavefront sensor they ever built, and play with it for about 3 months at my house, and I never could get it to do right, but it was still fun to play with.
Absolutely.
That's exceptionally cool.
No, that's amazing.
Yeah, it was fun.
AO is awesome. I've always wanted to work with it. Got a lot of that in Arizona, actually. It's part of the reason why I went there.
Yeah. Starfire Range in Arizona is where they built the first one.
Oh, wow.
It's cool.
That's amazing.
Very nice. Thank you.
Yeah, no problem. So, what should I do with the microphone? I'm so sorry for whoever's on Zoom because I totally just punched the microphone a few times.
No sweat. Thank you, Ryan. Thank you, Rhodes College, for not only hosting us tonight, but providing our entertainment. Wow. This was a knockout. This was, y'all did great. Thank you very much. This was at least as interesting as anything any of us would have come up with. And most of the stuff none of us ever worked on, we just read about. So thank you for sharing your work experience with those. Anything else anyone's got? We've got some outreach events coming up. Village Creek, Pinson Mounds. Well, Pinson Mounds is kind of
a little bit of a drive. But,
yeah.
We've got a special speaker doing the presentation at Pinson Mounds.
Oh, yeah. Yeah, very cool.
And also at Village Creek.
Yes.
All right.
You'll be seeing a lot of me.
Excellent. And then, of course, pay your $25 and come to the picnic. Let us know. I think we're going to send out an invite, and we need responses to know how many people are going to be there.
Tomorrow.
Okay, thank you. That'll go out tomorrow. So. What?
Glorious Galactic.
We are going to meet here, though. No. Okay, Zoom only next month. Okay. All right. What was the other question? Thank you very much, everyone. We really enjoyed it. Good to see you all again, and we'll do it again next month on Zoom.